Okay, so this 6.1 video is on density. And from a previous class, you might know that density equals mass over volume, which is the measurement of how much stuff is in a given area or space. So if you have more matter within an enclosed area, that's going to be greater density. If you have less matter in an enclosed area, you have a smaller density. And this mass is how we measure matter. We use this absolute, not weight, because weight is irrespective of, weight is totally based on gravity and the pull of gravity on a force, but mass is an absolute. So we recognize this idea of mass as a measurement for how much stuff is in a given space, and then volume is the assigned space that it's in. So we can make this more general by calling this amount over space. How much stuff and how big of a place. So now let's consider this as density is changing. Let's say that density is not constant. Porous rock, for example, is not constant. Some parts of it might be more porous than others. So if it's not a constant density, we can write how it's changing as a representation of the change in the amount over the change in space. How does the amount change as the volume of space is changing? And we give this representation a letter, rho, Greek letter rho, and this represents this change in density. Now, if we integrate d prime, then that means we're by space. So we bring that differential here up to the d prime, and we integrate d prime with respect to space. That means we then have the integral of the change in area. And if we do that, we can rewrite this as the integral of rho ds, because we've shown that d prime is the same as rho, so I change d prime to rho. And that is going to be the integral of dA. So therefore, the integral of rho with respect to the change in space is actually A. And so that's how we can find A. If we integrate rho, which is the change in density, the function that changes in density, if we can integrate rho, that should give us the initial amount. So the question posed to go along with this idea is find the total mass of a 4-meter rod whose linear density is given below. So linear density recognizes that density is not constant. It changes based on where you are on this rod, and the function at which it's changing is this guy. So this talks about how the density is changing over this area. So as before, we know that the integral of px equals the amount. So if I can integrate this linear density, I will get the amount, because I'm taking away how it's changing. So the integral of 1 plus cosine pi over 2 x dx. And we need some bounds, and that's where this 4 meters comes in. 4-meter rod. So we're taking this from 0 to 4. And to do this, we're going to need to integrate two separate ones. We'll need to integrate dx from 0 to 4. And dx the 1 plus the integral of cosine pi over 2 x dx from 0 to 4. That's going to be so I can u sub. So u equals pi over 2x, du equals pi over 2 dx. So I can do this one really quick. X from 4 to 0 plus the integral of 2 over pi cosine of u. And if I plug in, I can change the bounds to be 2 pi versus 0 to u. So that is x from 4 to 0 plus 2 over pi, and that is going to be sine of x, or u, 2 pi to 0. Just shrink this down. All right, so then this is 4 minus 0 plus 2 over pi. Sine of 2 pi is 0 minus 0. So I get a total of 4. And that is the amount, total mass. They didn't give us a unit, just that it's meters in terms of the measurements. So no idea on the amount. So I guess we just leave it without the units at 4.